In this video, we will talk about how to link libc base address via the global offset table. And this is especially for the case that we are talking about in last week's lab. So in last week's lab, we already have the libc base address, which I offered to you during class. However, it's very uncommon that we have the base of libc when we are launching the actual attack. So today, let's talk about how to get the address directly. So before we talk about how to leak the address of the base of libc, let's first go through the challenge that we had for last week. Right now, I am showing the source code of the service. So the service is composed of two functions, function main and function check. Function main calls function check. And then if you look at function check, you'll be able to find that a vulnerability exists over here in get because get doesn't check the length of the input, and it will just directly stores the input to string ID with the length of 50. So it means that if we are going to send a string that is longer than 50, we will start to overwrite the stack, and then we may be able to overwrite the return address of the stack. So now the question is, how are we going to overwrite the function of the start in order to get the base address of libc? And if you still remember the attack script that we have last time, we call the process, or we just connect to the remote server, and then we send this wrap gadget, and this wrap gadget chain composes the information that will execute bin message. And we use, like wrap gadget finding tools such as wrap gadget or wrap PM to find the location of those gadgets that will make RAX equal to hex3b, RDI points to string /bin/sh, and RSI is equal to 0, and RDX is equal to 0, so that we'll be able to call execv with the correct argument. So we already find those gadgets together, and we already connected together. But here, for every gadget, we are at the gadget location with base. And here base is the base address of libc when it is loaded into the memory. And here I am giving you the address of libc, right? Which is this argument base with the value of, hex 7ff7dd for 000. So in this video, our task is to find out the value of base instead of having this as default. Once we have the address of base, we will be able to use the rest of the tag in order to get an interactive shell, and we will be able to use touch statement or whatever statement to log in the participation. Now I'm going to close up this file and open a new file, and we're going to start from scratch to leak the address of the base of libc. And similar to what we have done before, we first start write to the main function, and in the main function we're going to connect to the remote server or initiate a local process with the correct linking libraries. So what we're going to do is first, again, its name is equal to main. We're going to construct the main function. And then we're going to define the main function over here. And for the main function, we'll first initiate the process. And in this case, we're using glibc 2.31. And the binary array corresponding with the service is called stack. And we need to specify the environment so that the correct libc will be loaded. So this is the way that we will be able to run the binary with the correct library locally. We can also connect to the remote server with the correct port. And you could use either of those two. And of course, for this, we need to use point tool. All right. Now the task for us is to send the right input so that we can get the address of the base of libc. Remember that in previous video, we mentioned that, the base of the libc, although it's going to change all the time because of the setup of ASLR, although in this case, we disable ASLR. But still, to leak the base address, we can have first get the address of any of the libc function. And then, since the library of libc is given, we can calculate the offset of that particular symbol, or say the function in libc, in terms of the base address of libc. So in that case, we will be able to get the base address of libc as long as we have the function address of a particular libc function. We can link whatever libc functions that we want. Right now, I am going to just choose a function called, put. And this is because that we know that when this function check returns, function put will be executed already. So in the got table, it will store the correct value of function put. I'm going to write a comment over here, the goal to leak function address of put in libc. So here there is put symbol in the PLT session. Okay, so now what we are going to do is to come up with a chain, especially a wrap chain, in order to leak the function address of puts in libc. As we already know, the function address, the address function puts, is going to be stored, which is stored in the global offset table. So where is the GOT? Where is the global offset table? Where is the entry for put specifically? In order to get that, we need to disassemble the binary, and we can get that information by looking at the PLT section. So here we found that this is the PLT section for put, and the location of put, function puts pointer is stored in 601018. So now we know that we need to leak the content that's stored at location hex 601018. To leak the content at address 601018. Okay, so how to do that? Since we have to leak it, so we have to print that location so that when we, as the attacker who interacts with the server, will be able to get that information coming from server. So the next step is to think about to print the content at location of hex 601008. And how to do that? The answer is we just use this exactly puts function. So what we're gonna do is to call puts and then with the address of 601008. Now we have a very clear goal, which is to let the rob chain to call function puts with the argument of hex 601018. And now we can work on this, think about how to come up with the rob chain. Let me just right now write the high-level structure of the code. So suppose here we're gonna return a string. We're gonna come up with the string. I would say construct string attack, and then this function is gonna return the attack. So we're gonna glibc and then use that. Now let's come back to this function specifically and then try to link libc base address. So again, let's do this from top down. Suppose that we're gonna have a chain, and this chain will be able to call puts with the correct argument. So suppose we were to have this chain, and now in order to trigger the vulnerability and make the attack successful, we need to have attack to overwrite the buffer. And last time we already figured out to overwrite the buffer, you need to have the buffer longer than 72 bytes. So we're going to have a padding. And now since I'm using Python 3, I'm going to put byte over here times 72 and then plus the chain. For the chain, what we are hoping here is that we want to make the chain to call puts with the correct argument. So first, let's figure it out how to make the argument correct. We need to make sure that the first argument, which is stored in register RDI, has to be equal to the value of hex 601018. A way to do that is to use pop statement. So suppose we're making the value over here is hex 1018. And then we're going to have a pop RDI statement, which will pop this value from stack. After that, we're going to run plt puts. And because register RDI is already stored with the correct value, puts will call with the correct argument. So in this case, we should have the chain with, first of all, pop RDI, so that when function return, it will jump to the location of popping RDI. And then when we go to the instruction of pop RDI, we need to put the correct value on the stack, which is hex 601018, so that when instruction pop is called, the correct value will be copy-paste to RDI. And then after the returns, we need to put the value of puts instruction so that now the instruction, the execution will jump to the instruction of plt put. Okay, so for put, we already know where it is. Let me just disassemble this again. So we know the value of put at PLT session is 400,5C0. 400,5C0. Okay, and now we need to find the gadget that will enable us to pop RDI. And remember that this time we cannot find this gadget from libc because this is like a chicken egg problem. We don't know where the libc stands, and that's why we have this libc. But if now we are going to use libc gadget, we have to know the base of libc in order to call it correctly. But again, we don't know it. That's why we cannot use libc. In this case, I'm going to just find this gadget from the binary directly. And I'm going to use ropium to find the gadget from the binary. To use ropium, you need to load the binary first. After it's loaded, you can find the gadget that you want with a specific condition. And in this case, we need RDI is equal to 601018. Okay, so it will tell us directly that what we can do is to put the gadgets to chain as first this pop RDI return, and then followed by the value of RDI that we want to put. So here, when we really want to make the value of the rob chain is equal to 400 hex 400 8B3. Now we have the entire chain, but remember, we're not formatted correctly, and we need to fit all the value in little endianness. So the way that we do that is we can actually use this nice function called P64 impoundlib, and it will help us sort it out. So all we need to do is to have the P64 function, make that as the conversion function. So in this case, once we call program stack and triggers the vulnerability, when function returns, it will call put with the correct address, and it will be able to return us something. And let's try to run this now. Okay. So now it's finished, but it doesn't print anything because we haven't put any print in our code. So we just sent the line with the attack, but it seems that it's fine since there's no segmentation fault popping up from this run. And then now we're gonna just print whatever received. Cool. So now we see something very interesting. This is the address for function put. And now all we need to figure out is the offset of function put in terms of the entire libc function. To get that, we can use optdump again to get the symbol of put in libc. And we can just search put. The offset of put is hex 87580. Next, we need to calculate the base address based on the offset. And that is pretty straightforward. We just get the byte sequence of function put, and then we're gonna calculate the base as this address. Actually, I need to strip it since there is a new line symbol at the end. Little. And then have this deducted by hex 87580. And let's try to print it. All right, now we got the base address. And you may notice that this base address is different from what I have given you in last time. And this is because right now, I am running the entire process in my own local machine. So the base address that is loaded in my own machine is different from that is loaded from server. Now let's change this from local to remote. And run this again. Cool, now we get the base address. Let's go back to the original demo. And we found that the base address is exactly what I have given you last time. Now, you will be able to connect these two pieces together and have a complete attack on the challenge. Have fun with it.